Welcome everyone. In this video we are going to derive the mirror equation. To start our derivation, I will draw a mirror. So we have the principal axis of the mirror that goes through its middle. It makes a symmetrical shape on both sides of it. And then we have our mirror. If this part is reflecting, if that is a reflecting surface, then this will be a concave mirror. If the other way is reflecting, then it is a convex mirror. So we have a concave mirror, and let's say that we are interested in a light beam and a ray of light that is crossing the principal axis at this point, perhaps. Okay, so we have a light like this, a light beam actually. And also I should draw the center of curvature, the center of the imaginary sphere that our mirror is a part of. Let's say that this is the center, which we denote with a capital C. And as a result, the distance from the center to any point on our mirror will be the radius, and let's denote it like this. It is going to be small case r. This is the radius of curvature. So we know that the light will be reflected in such a way that if we draw a line perpendicular to our mirror from the point of from the center of curvature, which we call the normal line, then the reflected light will make the same angle with it before and after the reflection. So the angle of, let's call this, this one perhaps theta, the angle of incident is the same as the angle of reflection. So, how does this help us? And also, what are we trying to find actually in the mirror equation? What is it? It is an equation that relates, if we call the distance that our point, this point, the point where the light beam crosses the principal axis, if we call that point and the distance, if you call the distance between that point and our mirror, if you call that distance A, and if we call the distance between the point where the reflected light beam passes the principal axis and the mirror, if we call that distance B, we're in fact looking to relate A and B. And perhaps you might have another quantity, as you will see at the end. So I want to write a couple of more angles. I will define a few. So I want to define this angle as alpha, and I will define this one as gamma, like this, and one last but not least, this one will be beta. Okay. And also I will define a length, a distance. I want to call this height delta x. Okay, it is the height from the point where the light beam touches our mirror to the principal axis. So, excuse me, so this length is named delta x from now on. Now, if you look at this picture, I want you to understand delta x here is a small value. This goes to 0. We are only interested in small values of delta x because otherwise our equation collapses and we can't make our derivation. And you will understand why that is the case. So if delta x is a small distance, what happens to our angles? Well, this means that all our angles, theta, alpha, gamma, and beta, they are all angles that are close to 0. Because if you have all this system and if you have it going to 0, if delta x goes to 0, then you can picture it in your head, I hope, that these angles also go to 0. They become closer and closer to horizontal. They get closer and closer to the horizontal, to the principal axis. All right? And if we have a triangle like this is just general geometry. we will use this. If we have a triangle like this, if this angle is theta 1 and if this is theta 2, and if you're asked about this angle, it is going to be theta 1 plus theta 2. And how do I know that? Because this angle is 180 degrees minus theta 1 minus theta 2. The interior angles of a triangle should add up to 180 degrees. So that is how I got this green value. And this should be supplementary angles. Their sum should be 180 degrees. So this angle has no choice but to be equal to this plus this. Okay, that was just a side note. I will actually erase this. And using this result, I will now express gamma, in terms of alpha and theta. So gamma is here. We have alpha, we have theta. It is the same picture that we just had. So we can see that gamma is equal to alpha plus theta. And if I want to this time express beta, I will similarly say it is going to be gamma plus theta. Alright? Now using well, let's see, what could we do here? Perhaps we could say, let's solve for theta in both of these equations. Okay, and why not? Because theta is the only thing that is common. Well, actually, there is gamma as well. You could do the same step for gamma then. I just noticed that. But I will do it for theta. So theta is, from the first equation, gamma minus alpha. And also, I really would like if you tried doing this same derivation with using gamma in this step. Let's see what happens. And now we have theta. From the second equation, it is beta minus gamma. Alright? And of course, this theta and this theta, well, they are equal. They are the same theta. They are the same angle, which means, let's write it with red, gamma minus alpha is equal to beta minus gamma. I just set these two equal to one another because they are both equal to theta. So if we solve for gamma right now, we will get 2 gamma is equal to alpha plus beta. This is great. We will actually use this in a couple of minutes, I hope. But now I want to return to our picture and I want to express delta x in such a way that I have a. So how can I represent it? Well, if I have a, then I should multiply it with tangent of alpha, right? Because look at this triangle, this blue one. Tangent of alpha is opposite, which is delta x, divided by the adjacent, which is a. So if I multiply both sides by a, I get delta x is equal to a times tangent of alpha. And if I consider a smaller triangle like this one, perhaps the one in green now, then I can say delta x is also equal to r this time times tangent of gamma. Alright? And we can do one more like this. We can say this is also equal to, this time b, we are looking at this little triangle, b times tangent of beta this time. Alright? And my friends, this is where the small approximation, this part, comes in play. We will now substitute alpha for tangent of alpha, because if we have small angles, then we can say, if we have tangent of theta, where theta is going to 0, then this is going to give us theta. Okay, because sine of theta approaches theta and cosine of theta approaches 1 as theta approaches 0. So tangent theta, which is sine over cosine, should approach theta. This is just an approximation for tangent of theta. It is not exact, but since we are interested in the limit, we can make this approximation. So I now substitute that. I have a times alpha is equal to, and of course the letter that we use to represent an angle doesn't change the mathematical result. So we can say r, and instead of tangent of gamma, we can write gamma. And we have b, tangent of beta, simply we can write beta. Now, if I consider, if I express alpha and beta in terms of gamma and other lengths, then I can get these equations. If I say alpha is equal to, well, focus on this part. If you divide both sides by a, you're going to get r over a times gamma. And now if I want to solve my equation for beta, I can focus on this part. And if I divide both sides by b, I am going to get r over b times gamma as my value for beta. Alright, and we are very close to the end, my friends, so please stay tuned. This is the important and interesting part. So if we return to this identity that we found, that 2 gamma is equal to the sum of alpha and beta, and if we substitute for alpha and beta these values, this and this that we just found, something interesting is going to happen. And let's do that on a new page. So we have 2 gamma is equal to, as I argued, alpha plus beta. So substitute for them. Let's substitute. For alpha, we're going to write r over a gamma. R over a gamma plus. For beta, it is right here, r over b gamma. So let me write it. R over b gamma. And as you can see, this angle gamma is gone. This is great. And now comes the interesting part. If I divide both sides by r, which is the radius, I will have 2 divided by r is equal to 1 over a plus 1 over b. I mean, this transition was a little quick, but I hope it makes sense. And if you would like, you can pause the video and convince yourself that if we divide by r, the above line, we actually get the below line. Okay? This is not a sad face, this is division by r. We are all happy. So, I mean, you might be asking, how does this help? Come on. Well, I want you to realize something. What is 2 divided by r? What is 2 divided by r? It is going to be the reciprocal of the focal length. 1 over f is its value. And if you don't know how this is correct, you're asking perhaps, then I have a video about this. You can find it from the cards right now. It comes from the fact that, as I proved in my previous video, in one of my previous videos, f, the focal length, is equal to r over 2. And if you rearrange this, you get 2 over r is equal to 1 over f. So we can substitute this. If we do that in red, we will have 1 over f is equal to 1 over a plus 1 over b. And boom, this is the mirror equation. This is, my friends, very helpful. We will use this a lot in optics. But I want to add a little thing. This is the mirror equation for a concave mirror. Concave. Because remember, we started our derivation with stating that our mirror was a concave mirror. For a convex mirror, the result will be very similar, only there will be negative signs. Alright, and you might be asking, what kind of negative signs? Well, it will be in such a way. You will determine it like this. If you have your principal axis and your mirror, this time this surface is reflecting, so this is a convex mirror. If you send a light like this, it will perhaps reflect in such a manner. Well, it never actually crosses the principal axis, so how can we find a value for A, you might be asking. And to find a value for A, we consider the imaginary extension of the coming ray. So if we extend the direction of our ray, direction of the light beam, it would cross the principal axis at some point, and this point will be our A value. However, since the light doesn't actually cross it, only its extension crosses it, we make this a negative A. Okay, so we substitute negative A for A here. So when do we substitute negative A or negative B? If the light beam is not passing through the principal axis, if only the extension of it is passing through, and of course for the focal length of convex mirror, we know that it is going to be negative because again the convex mirror's focus point is behind the mirror, so we represent behind as negative. That's why we put a negative for the focal length as well. So what I am trying to say is, to make our formula general, we can put plus or minuses like this. Let's do it with a different color so that it looks nice. So don't forget the plus and minus here. And now this is a general result, and this concave thing is gone. So this is the mirror equation. It is very important to be careful while deciding on which is positive, which is negative. So be careful about that. But anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.